Okay, this recording is for the 1-act people who are gone today. This is section 5.2, the backside, the last like 3 examples, I think. We're on story problem number 5. Yesterday, we did one of the story problems, and I told you how to find it, like approximate it in part B. This was just an approximation. We just plugged it in and tried to look at our table to figure out when it reached $8,000. I'm going to show you in the next example how to find it exactly, okay? So that's why my little calculator's out over here. I'm going to show you how these buttons work and everything. So population growth. Based on data from the past 50 years, the world population in billions, underline that word, in billions. Anytime they give you units, make sure you underline it. Sorry, we're really delayed if you're watching this video. In billions, underline in billions. Anytime they give you units, underline it. Can be approximated by the function blah, blah, blah. This is a growth function, okay, because the number that I'm taking the variable to is a number that's bigger than 1. So it is a slight growth, 1.01 or 1.02 is slightly bigger than 1. Estimate the world population in 2015. So how can I do that? Plug it in, but I'm not going to plug in 2015 because 0 is 1950. Year 0 is 1950. So what would the year 2015 be? 65. So I'm going to plug in x equals 65. Plugging in 65. You guys see why that is? Plugging in 65. Okay, so on your calculator, practice typing that in. 2.5 times 1.0185 to the 65th power. To the 65th power. Do I need to do it? I'll do it anyway. 1.0185. I type in so slow. 65. Like that. Enter. 8.23. What the heck does that mean? 8.23 billion people in the year 2015. I don't know, what are we at right now? Oh, we haven't reached that far yet. Okay, so this is a little bit off, Okay, now this is the important part, and I'm going to tell you how to do this without approximating. We're going to get an exact answer for this, okay? In what year will the population be double what it is in 2015? Okay? In what year will it double what it is in 2015? So if I take this number and double it, we need to figure out what that is. Okay? Taking this guy, doubling it, times 2. 16.46, yeah. I want to know when this equation, my beginning equation, will be 16.46. I want to know when that will happen. So what am I solving for? I'm solving for x. X is really your time period, right? X is t. That's kind of like your time. Right? I'm trying to solve for time as a t. So I'm going to solve this, and I'm going to get an exact answer. I'm not going to approximate it. I'm not going to graph it. I'm not going to do anything like that. I'm going to get an exact answer. Here's how you do this. Okay? Thanks, Kate. Go away. Hurry up. Hurry.
Hurry up, you slob.
Music to my ears.
All right. Hayden, hurry up. I don't care. Then use a different pencil. All right. So I want to simplify this as much as possible. Listen. I want to simplify this as much as possible and isolate the x. So what can I move to the other side? How can you move 2.5 to the other side? Divide by 2.5. Divide by 2.5. Okay? All right. 16.46 divided by 2.5. What is it? 6.584. Equals 1.0185 to the x power. Okay? And I want to solve for x. But the problem is x is in the exponent. I can't just like divide by 1.085. Okay? I can't just do that. So here is the rule. Yes. Here's the rule. Okay, we did this probably in algebra. Listen, we did this in algebra probably. But this is an exponential function. Okay, these are all exponents, and the inverse of exponents is a log function. Okay, is a log function. So what we have to do to get him out of there is put a log in front, okay? And I'm going to use a special type of log. I'm going to use what's called ln. So I'm going to do ln of this thing, and I'm going to do ln of this thing. Okay? And because you do it to both sides, it works, all right? Now, there is a special rule with logs that says as soon as I put a log in front of something, this exponent right here can come down in front. Okay, that exponent can come down in front. So really what this is doing is saying x times ln of this stuff is equal to ln of this stuff. Okay, and I can do that, all right? Now, can you get the x by itself? How? Yep, divide by ln. Divide by ln 1.0185, and that cancels out. ln 1.0185. Okay? Now, here's an important part. Even though both of them have an ln on the top and the bottom, you cannot consolidate it into one. So this, do not try to type in your calculator. Don't do this. ln of this stuff over this stuff. It's not one ln. Don't do that. Don't do this. Okay? Don't try to cross out the ln's and do ln of 6.584 over 1.0185. Okay? You have to put an ln on the top and on the bottom in order for it to solve. Okay? So what is x equal to? 102.8. Okay, we got an exact answer, but what does that mean? What does 102.8 mean?
No, that's the.
This is year.
2015.
This is year 102.8, right? Okay, but that's years past. Yeah, that's years past 1950. So if I add that to 1950, this would be 2052, and then 0.8. So like September or. What is it, August?
We
No,
forgot the time of the
that.
day and the month of the.
I know. We get it the day and the month.
Shut up.
Like what your sister used to do that. Riley used to do that all the time. She would figure out the day and the month and the year and blah, 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 all that stuff. So, 2052. About halfway through the year 2052. There it is. Okay, there he is. All right, let's go to the next one. Radioactive decay.
What?
The amount of 1 kilogram of plutonium that remains after X years can be approximated by the blah, blah, blah. Estimate the amount of plutonium remaining after 10,000 years. What's that asking you to do on number 6? Just plug it in. This one's asking nothing more than just plug it in. This is years. 0.99997 to the 10,000 power. What is that?
0.741.
0.741. Okay, so this is like 74% of it is remaining after 10,000 years. That takes a long time to break down. Plutonium does. I don't know what plutonium does. All right, next. This is an important number that you need to kind of remember or recognize at least a little bit. E is kind of like pi. Okay. Well, you don't have to remember it, but just remember like 2.7 is. Okay. So pi is 3.14, blah, blah, blah. E is another number kind of like pi. It's just a number. 2.7182818, blah, 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 and it goes on forever. Okay? And I don't know. Why don't we have an E day? I don't know. The number E is a naturally occurring number. This is where it comes from. The number E is a naturally occurring number that occurs with compound interest. So people who work in the banking system probably have computers to do this for them. Listen. Probably have computers to do this for them, but their computer systems work in like base of E, basically, okay? Because compound interest is base E. So, population growth. Here we go. Estimate the population in 2015. This is our equation right here, okay? So we're going to be plugging some form of 2015 in there, but we're not going to plug in 2015. What is year 0? 0 is 1980. So make sure you pay attention to that. 0 is 1980. So what's 2015 going to be? What? 35? So x equals 35, or actually it's t equals 35, whatever. There is an E button. I'll show you.
Oh, that's good.
Okay, so T equals 35. All right, now, just plug in 35 in for T and we'll see what we get. I will show you where your E button is. Hold on, I will show you where your E button is. Okay, so if you type this in on your calculator over here, on, clear, 227, I'm going to do E. The E button, if you have a scientific calculator, is the LN button. It's like on the very, very left side down, like 3/4 from the bottom, LN. You have to hit second LN, and it is E, and mine automatically raises it to an exponent. Okay, and then you just type that in. So 0.0093 times 35. Okay, anybody not able to find their E button? Okay, 314 point something. 314.33, you're right. And that is the approximate population in what? In 2015, but what units is it in? Millions. In 2015. So according to this model, they've approximated our population, or whatever the population of what we're doing. Population of the United States. So not the world, but the population of the United States. They are approximating it to be 314 million in 2015. I don't know what it actually was, but pretty close. Okay. Okay. When will the population reach 500 million? Okay. So when will the population reach 500 million?
His pupils or his eyes?
Okay, be quiet. Be quiet so we can get done. Okay. When will the population reach 500 million? We're trying to solve for T, but what do I set it equal to?
500.
500, right? 500 million would be 500 million, yeah? Okay, and since we're going in millions, we have to put that in terms of millions. So 500 million in terms of millions is 500. Okay, now what are you going to do first? Divide by 227. 500 divided by 227. What is that decimal? 2.2. Exactly? Give me another one. Okay, we'll do this 2.20. Equals e to the 0.0093t. Okay, now this is the beautiful part. To get that t out of the top, you would have to natural log both sides, or log both sides, right? Okay. When you do ln, it gets rid of e. Like there's nothing there, right? So when we use ln and there's an e involved, these two just go away. Like there's not an e left in the equation. It's just that. So we have ln of 2.2 equals 0.0093t. And how do I get t by itself? 0.0093 divide by 0.0093 on both sides. Okay? Now, if your calculator opens, listen to this, if your calculator opens a parenthesis, when it does the ln button, make sure you close it after the 2.2. Okay? Right? If your calculator, when you type in the ln button, opens a parenthesis, you're going to have to close the parenthesis to do 0.00 whatever. Okay? So ln is this button down here, like the E. 2.2, I need to close it. 2.2, close parenthesis, divided by 0.0093, enter. There we go. Is that what you guys got? T equals 84.78. Okay? And that is years since 1980. So if I add that to 1980, what will that be? 20, is it 2064?
Yeah.
2064.78. So about halfway, a little over halfway through the year of 2064.78. I don't know.
Who cares?
Maybe July or August. July or August. I don't know. Take 0.74 times 12. Or take 7/8 times 12. Somebody do it. Take 7/8 times 12. 9.36. Okay, so this would be September. Okay, now 0.36.
Move on. What
You
else?
want to keep going.
I want to figure it out.
0.36 times how many days are in September?
30.
30. What's 0.36 times 30? 6. Or 0.36 times 30?
10.8.
What?
10.8.
10.8? Okay, we could do the hour, but we'll just say 11. So it is September 11th of 2064. We could do the hour, the exact hour, if we did 10.8, but whatever.
9/11.
9/11. Oh my God. On 9/11 in 2064.
Well, because I don't want to do the hour.
Technically,
I don't want to do the hour.
Technically, it'd still be 10.
It'd still be 10 though, yeah.
So why did you say 11?
I don't know.
That.
We rounded.
It's not
We
11.
rounded. Whatever. So September 11th of 2064. We don't care. We don't care. All right. Let's skip example 8, but I want you to go to the back side and
Why'd you cost 9/11?
we don't care. We don't care. Okay, go to the back side. We got to talk about even and odd real quick. Even, odd. Okay, this information is way back from chapter 3, but I'm going to give it to you now because they ask you some even odd questions. So even functions are like x squared, x to the 4th, x to the 6th, blah, blah, blah. Even has a certain type of symmetry. What? Line symmetry? How? Like what line? What is he symmetric about? Like x squared is a parabola.
Oh, why?
He's symmetric about the y-axis symmetry. Something is symmetric with respect to the y-axis if you can plug in negative x and y, and it makes like the same thing, right? So an example of that would be y equals x squared, right? If I plug in negative in for x, y equals negative x squared. Negative x squared is the same thing as positive x squared, because when you square a negative, it becomes positive. So he has y-axis symmetry. We have checked it. It turns into the original. Does it turn back into the original? If it does, it has y-axis symmetry. Or it is even. It is an even function. Okay, odd. What type of symmetry does odd have? Origin symmetry. Okay, so it is symmetric with respect to the origin, like y equals x to the 3rd power, which looks like this. Okay? Whatever's in the 1st quadrant is also in the 3rd quadrant, and etc., right? What's the rule? What do you plug in? Yep, there are negatives for both. Yeah, negatives for both. So let's check. Y equals x to the 3rd power. Let's check to make sure. So we're plugging a negative in for y, and we're plugging a negative in for x. Okay? If I take negative x and cube it, does it stay negative or become positive? It stays negative. So I have negative y, negative x to the 3rd power when I pop him out. Is that the original? If I divide both of them by a negative 1, now he is the original. So it turns back into the equation. So he is an odd function. Does that make sense? Yeah? Okay, there you go. That's just a review from chapter 3 on even and odd, yeah? Okay, there you go. All right, closing the video.